started on this second section. We're just going to work our way through it. And I think what I'm just going to do is we're just going to go through today, we're going to go through Thursday, and then at the end of Thursday, I'll make up a video for if anything doesn't, if we don't, cover it all essentially, right? So that's my plan. And just as I said that, Jessica, you are here. Okay. I just saw another Jessica up here. Looks like Zoom's being weird. So what we're going to do in this section is we're going to essentially look at the calculus of vector functions. In other words, how do you differentiate and integrate them? And what can you do with these derivatives and integrals? And there's going to be, 7 main topics. So I want you to imagine that this is a typical space curve in 3D, right? The analogy I like to give for what we're about to do is a roller coaster. So can you imagine this is a roller coaster doing its thing, right? Now, if you want to find the derivative of a vector function, also called the space curve, let's imagine that it's written in this generic form. R of t is x of t, y of t, z of t. So it's like t squared, comma, sine t, comma, e to the t. Remember, we did a little bit where we did it online. You could see the cool curves, right? The helix and so on. So you've got a space curve, right? Which is this guy here. If you want to differentiate the space curve, you get a vector function. So this vector function, when you differentiate it, generates what's called the derivative vector function, r dashed of t for short. How do you think you're going to calculate it?
Derivative of each section.
So again, Jeremy?
The derivative of each section.
Yes.
X, Y, and Z component.
One component at a time. Isn't that nice that it's actually intuitively, it kind of makes sense, doesn't it? I mean, it seems sensible at least. And that's what you do. So, for example, if my vector function was t cubed, t squared plus 1, e to the t, just for argument's sake, and I could put that in and show you in GeoGebra, right? Spiraling and curving, doing its thing. To find its derivative, we really just do Calc 1 stuff. We do it 3 times. You differentiate each of these individually. So you would get 3t squared, 2t, and then e to the t. So how do you interpret a derivative vector? I mean, what does it kind of tell you? Well, let's imagine that I found the derivative vector at 1. Then this would be 3, this would be 2, and this would be e. Do you see it's just a vector, right? And can you imagine that on this space curve, this roller coaster, that's where you are at t equals 1, right? You're right there. If I drew that vector, it would look something like this. So I want you to imagine that you're on a roller coaster. And at that point there, the roller coaster is broke. This vector is a vector that you shoot off to your death in. Do you get the idea then? That what a derivative vector is doing is essentially telling you the direction the curve is pointing at that instant in time, right? At t equals 1, where would I go if the track disappeared, right? I'd shoot off the edge, but wouldn't I shoot off the edge in a vector? Now, the length of that vector, if you measure that, right? If you find the magnitude of it, the length of that vector, and I'll make it a general version right now, the length of that is actually the speed at which you shoot off to your death at. So you shoot off in that direction at 40 mile an hour, or you shoot off in that direction at 500 mile an hour, right? You're shooting off at that direction. Now, can you imagine then if you were looking at this as a jet traveling and it fired a missile at this point, and it wasn't one of those intelligent missiles, right? It was just a fire, and it kept on going in whatever direction you were going. Wouldn't this vector be the path of the rocket as it left the aircraft. So what we've got here is a way of finding derivatives, and the magnitude of the derivative represents the speed of that moving object, and the vector at that point gives you what we call essentially a direction vector, right? The direction that you would shoot off. And we can use that in lots of different ways to model essentially moving objects. Are we good so far? Any questions? Right, there is a bunch of questions, numbers 1 to 5, where what you are doing, or what you're going to do is, here is your vector function, find its derivative. So as long as you remember your Calc 1 derivative stuff, you should be good to go. So I'm just doing a kind of combination of situations. So we'd have the square root of t minus 5, and then we have 7, and then we have 4 over t squared. And what you need to do is differentiate each one of these separately. Now, I would probably do this kind of at the side. This is like my working. And then once I've finished it all, I'm going to write the answer here. Okay, this guy is the square root of t minus 5. If you want to differentiate, yeah, you have to do it as half power. Agreed?
Shouldn't it be x equals?
Why did I call it y? Oh, because I'm just, yeah, you're right. I'm into my old habit that y is the main function, y is a function of x and y, that sort of thing. So it's x equals. Now, if you differentiate it with respect to t, we'll use that notation, it's essentially a chain rule. So it's 1/2 t minus 5, reduce the power by 1, and then differentiate by the inside function, which doesn't do anything because it's just 1. And then you make it look pretty by bringing the t minus 5 to a half of 1. And then to finish the style points, you make it look like the original. So there's our first piece of the puzzle. We got that guy. I'm not going to write the working for the second one. What would you get if you differentiated the number 7? With respect to t, what would you get? Come
0.
on, 0. I know it's a silly question, but whatever. Z is 4 over t squared. If you're going to differentiate this, you need to rewrite it as a power. So 4 over t squared can be written as a negative power, right? 4t to the negative 2. That means I can now do the power rule. So when I differentiate it, I get negative 8 multiplied by the power. You reduce the power by 1, and then you make it look like the original at style points. And there's our answer. So the derivative of this vector function is that guy. Are we good? Really, aren't you just doing Calc 1 differentiation 3 times? It's really all you're doing. Now, how about, let's see if we can find something a little bit more meat to it. What about question 3? So the space curve that we're going to differentiate this time is t cubed, the cosine of t to the 5, and the sine squared t, which I'm going to write like that to make it easier to differentiate. Okay, here's the derivative. Power rule, multiply by the power, reduce it by 1. What method will you use to differentiate the cosine of t to the 5?
Chain rule.
Right, so you differentiate the cosine of this guy, you'll get negative the sine. That's what you get when you differentiate a cosine. Followed by the derivative of this guy, which is 5t to the 4. Now, the reason I wrote sine squared t in this format is to make it a little bit more obvious. Isn't that also a chain rule? It's a sine t being squared. So when you differentiate it, you will get 2 sine t's to the power of 1 times the derivative of the inside function, which gets me cosine t. And now I'm just going to do a little bit of style pointing, nothing too much, that's okay. This guy here, it makes more sense to put those guys first before you do the sine. And then I'm going to do that one with the trig guy. It says 2 sine t cosine t, right? That's what it says. But isn't that the same thing as the sine of 2t? So there are only 3 rules to making things look pretty, right? 3 rules that you typically would deal with. And most of the time you only use the first 2. Rule number 1 is make the answer look like the original, right? So if the originals get square roots, the answer should have square roots. That's rule number 1. Rule number 2 is factor the heck out of it, right? Which typically is not going to be an issue with these questions, but it is what you do. And rule number 3 is the hardest of them all. And that is, if it's a trig expression, try and find an identity, if there is one, that will make it look prettier. Right? And so that's what happened here. Now, in a lot of the cases, you may not be able to make it look pretty, right? 3 sine t plus 4 cosine t is as good as that guy's ever going to get, right? There's nothing you can do to that one. But sine squared plus cos squared gets you 1. Cos squared take away sine squared gets you to cosine of 2t, things like that. Right. Next one is not going to be any particular question. I'm just going to play about with pieces of different things. So for my last version of this, there's the first guy. There's the second guy. And there's the last one. We're going to differentiate each one of these in turn because we're going to find the derivative. And if the question warrants it, and it's up to you whether it does or not, you might want to do some of the working on the side. So that's the first one, right? That guy there. What method will I use to differentiate t e to the t? This is Calc 1 we're talking here.
Product rule.
So in the product rule, you call this guy f, you call this guy g, and the product rule is f dash g plus f of g dashed. So that's 1 times e to the t plus t times e to the t, and make it look pretty by just pulling out a common factor. And that's dx by dt. So first answer, e to the t, 1 plus t. What method will I use to differentiate that ugly fraction?
Do the convert it to the the t squared over plus 1 to the -1, then do the chain rule.
That will work. Nothing wrong with that. It's actually a nice way of doing it. That's the method I am going to use. Anybody want to tell me a different method that would also work?
The quotient rule, which is really long.
Which is really long, which is why I'm avoiding it, but it's doable. If you were going to do the quotient rule, the top guy is called f, the bottom guy is called g. And if you were going to do that rule, then it would be f dash g take away f of g dashed over g squared, right? Which is right, but you get it's kind of long. So let's look at this one. Multiply by the power, reduce the power by 1, times the derivative of the inside function, which is 2t. Then make it look pretty. Negative 2t, and bring that guy downstairs as t squared plus 1 squared. Would you agree that was a lot neater and faster than probably doing this? Right? But if you did this, you would get that as your answer. It's not like that's wrong, right? It's just a different way of doing it. So this one is negative 2t all over t squared plus 1 squared. And for the final one, what method should you use to differentiate sine cubed 2t minus 1?
Gotta double chain rule it.
You would. I call them Russian dolls. They're basically chain rules inside chain rules. So what you've really got is this guy cubed. So you've got 3 times this guy squared times the derivative of a sine, which is the cosine, times the derivative of 2t minus 1, which is times 2. Do you see it's like a doll inside a doll inside a doll kind of thing? So I call them the Russian dolls questions. Now to make it look pretty, really all I'm going to do is that, and that gets you 6. Then I put a single cosine and then a sine squared. The most common mistake that people do when you have these chain rule inside chain rule questions is they miss one of these guys. They either forget about the cosine one and just finish with a times 2, or they remember the cosine one, but they forget that there's an extra times 2 after that, right? They sort of a pseudo do it, but they miss a piece. So you put all of that together, you have 6, you have a cosine of 2t take away 1, and a sine squared of a 2t take away 1. And we are done. Do you feel comfortable about finding the derivative of a vector function? We feel good with this method, right? As long as you can remember your Calc 1 differentiation rules, you'll be fine. So let's check them off our list. Now we're going to do a guy called the unit tangent function. Capital T of little t. Right. So we're going to look at the unit tangent function. Pretty much every textbook's going to use that notation, right? Capital T, T for tangent, right? Now, what is the unit tangent vector, right? What is this guy? Is a vector parallel to the first derivative at 1 unit long. So imagine you get your space curve doing its thing, and this is the point where we're going to get right the derivative, right? You're shooting off to your death. The unit tangent vector will be at that same point, and the only difference is that its length is 1. Now, I don't know why engineers would want to know that, so I'll make up a lie that might seem reasonable. If you're really only interested in the direction, right, at various points, you don't want big directions and little directions. Do you think it might make sense if you just made all of the directions 1 unit long, and that way you're really just comparing like with like, right, direction with a different direction, but they're all got 1 unit long. So how about that as a reason to do it? I know you can actually use it when you want to do a coordinate axis, you know, like the X, Y, Z axes that we have. There is a coordinate axis system where you use the unit tangent, the unit normal, and the unit binormal. And they're like your XYZ, right? They're all orthogonal to each other. And they can be sometimes useful if you want to model a moving object that's got quite a complicated shape to it. Well, essentially what you do, well, let's show you one, so you do, is that you're going to be given a space curve, typically. How about t squared minus 1, t cubed plus t, 2t minus 1. And you'll be asked to find the unit tangent vector at some number, let's say 2. So this is the original space curve, right? The original vector function, and I'm going to find the unit tangent vector at 2. So you can imagine that guy, that guy there is where it is and t is 2. So here are the processes. Step 1. Find the derivative. And I've tried to make this nice and easy for myself. 2t, 3t squared plus 1, and 2. You all comfortable with the derivatives? Made the functions nice and easy to do. So far, so good. Right. Now, since you're interested in only the unit tangent at the number 2, then you could find what that vector would look like. 3 times 4. It would look like that guy. You see all I'm doing there is plugging in 2, 2, and that's obviously 2. So far, so good.
So it's all intuitive.
And I'm not catching what you said there. Sorry, Liz.
Oh no, that this section is basically all intuitive.
Yeah, makes sense. They're none too weird going on. Good. Things that are intuitive tend to be easier to do because they're easier to understand. Right, now the unit tangent vector. Well, how do I get that? Well, I kind of need to do the magnitude of this vector, don't I? So that's what step 2 is going to be, and I wish I hadn't written that thing down yet. Find the magnitude of this fella, which is, because I'm not good at picking questions to come out with nice numbers, isn't it basically whatever that thing is? And here goes in. It's going to be 16, I had 169 plus 4. Yeah, could have been worse. So the magnitude of that guy is the square root of 189. Now I'm ready to put the pieces together, which is the final step. The unit tangent vector at 2 is basically 1 over, that was a daft idea, let me put it down here. 1 over that guy,
Question, should the bottom be the magnitude of the
Yes.
value?
So in this case, it's going to be that guy times 4, 13, 2. And you stick them all together. You get that guy, and that guy. I don't think there's probably much advantage in rationalizing the denominator, so I'm not going to bother. Obviously, if that square root was a nice thing, like, square root 100, wouldn't I replace it by 10 and, do something like that. But that's essentially what a unit tangent vector is. You find the derivative vector at whatever the given point is. You then get the magnitude of it. And if you do that, it's simply, here it is here, then the unit tangent vector is 1 over the magnitude of the derivative vector. Now, as a formula, it looks like this. The unit tangent is 1 over the magnitude of the derivative, that's an r dashed of t. Is what you're doing, intuitive? Does it make sense? Right. So let's just pick a couple and call it good. I think there's about 5 questions, is there? Yeah, there's 5 to do. I'll probably pick a couple. Don't really care which ones I do because it's kind of random what you get. Turn it in space. There we go. I had some background sound, so hit the space bar when you want to say something. Which one shall I choose? No, I did the polynomial, so I'm not doing that one. There, another polynomial. I don't really want to do that one. Oh, this one. So, question 8.
I believe that your screen is not online, so.
Oh, thank you. There, I was closing something. There we go. So, question 8 is the one I've decided, or at least one like it. And it's chose it because it's ugly. Because the others were like 3t cubed and 4t squared. You could do them in your sleep. So this is the space curve, and we're being asked to find the unit tangent vector at t equals 0. So I'm going to take it slow. I'm going to differentiate each one of these to fit. So essentially I've got my derivative. Okay, that'll get some cobwebs going. What is the derivative of the inverse tan of t? I know it's not secant squared t. That's what the derivative of tan t is.
It is 1/1 plus x squared.
And in this case, t. But essentially what you said is right. So we're good with that one. Put a little bubble around it because I'll forget which one's which. The second one I don't think is a big deal, but since I'm doing them separately, I'll do this one separately as well. You're going to do essentially a chain rule. So when you differentiate this guy, you get 2e to the 6t times the derivative of 6t, which is 6. So you are going to get 12e to the 6t. Are you comfortable with that one? And the last one, 12t e to the t. You all recognize what's going to be a product rule. So we're going to do an f dash g plus an f of a g dashed. If you differentiate this guy, you get 12, leave him alone. You leave him alone, which is 12t, and you differentiate e to the t, and you get e to the t. So for style points, you can pull out 12e to the t, and that leaves you with 1 plus t, and that is dz by dt. So we now could do the derivative. It's this guy, and this ugly guy. And we are interested in the unit tangent at 0. So once I know this fella, I can find the derivative at 0. Well, that's 1/1, so that's just 1. That's nothing, either nothing's 1, 12, that gets me 12. And that's nothing, and that's nothing, so you get 12. How's it looking so far? We're good? So now I'll get the magnitude of this fella. So it's the square root of what? 144 plus another 144. So I'm glad I'm not the only one that has. Oh, I wouldn't believe that. That is amazing. Square root of 289 is 17. Oh, they deserve a prize. I mean, can you imagine how hard it is to get something to come out so nice, right? Okay, unit tangent then. 1 over the magnitude of this guy. And so that would be 1/17, 12/17, 12/17. We're done. I mean, it involves processes that you are comfortable with, right? Things that you've done in other places, right? You know how to differentiate, right? You know how to find the magnitude of a vector, right? You know how to get a unit vector. You just put those together, and what you end up getting when you're finished is what's called in this case, it's called a unit tangent vector. Let's see what I can get for the next one. Yeah. Do I want that one? Yeah, I'll do this one. So my last version of this is for a space curve with some trig stuff in it. And this guy is going to be cosine t. This guy is going to be 6t. And this guy is going to be 2 times the sine of 2t. And we are interested in the unit tangent vector at 0 because they have no imagination. Couldn't have got the unit tangent vector at pi over 2 or 49 or something, but no, they want 0, probably because the numbers will come out nice, I suspect. I'm now going to differentiate, and I think this one I can do without extra work at the side. You differentiate a cosine, you get a negative sign. You differentiate 6t, you get 6. If you differentiate this guy, it is a chain rule. What you get is 2 times the cosine of 2t times the derivative of the inside function, which is another 2. So you are going to get negative sine t, 6, and 4 cosines of 2t. Are we good? Right, now, the derivative at 0 is negative the sine of 0, 6, 4 times the cosine of 2 zeros, which is still 0. That guy is 0, that guy is 6, and that guy is 4. And there is your derivative at 0. Now we'll get the magnitude. It's going to be 0 squared, 6 squared, 4 squared, which is the square root of 52. Can't do anything with the square root of 52.
You could make it into 2 times the square root of 13.
Yeah, okay. It's best I can do, right? Can't think much else. Right, so the unit tangent vector is going to be 1 over that guy, a 0, 6, 4. That over 0 is still 0. That over that, well, you reduce it a little bit. And that over that, you reduce it a little bit. Are you happy with our unit tangent vector? Any questions about that? Anything you want me to talk about, or can we call that group of questions done? So if I give you a space curve and I say I want the unit tangent vector at 0 or 2 or pi, you're comfortable about the process. Okay, and I like that. Things floating around here. Start being neater. Check off my list. Now, there's a one-off question, number 3. Question, pardon me, number 11. which asks you to just do various calculations using the derivatives. In particular, finding the first and the second, and finding the cross product. They also stuck in a unit tangent vector at 1, but I'm not going to worry about that. That's a special case. Let's just focus on these guys, right? So, the function that I have, where we're going to calculate all these things in terms of t, right? So we're not going to replace them by a number. Is for this guy. And the style points is going to be the killer here, making it look pretty. Let's get the easy ones out the way first. The first derivative is just multiply by the power, reduce it by 1. 1 multiplied by the power, reduce it by 1. Would you agree there's nothing that hard to do that? And I wouldn't say the second derivative, although I've not mentioned it yet, is also intuitive. But let's just talk about it for a second. How do you think I find the second derivative? I mean, if the world was fair and all math was logical, what should I do?
You just do the same thing with the first one or the first derivative.
Agreed? And that's what you do. Isn't it nice when math actually makes sense and it does what you wanted it to do? Now, the third one of this is where it gets really decidedly weird. We are going to find the cross product of that vector and that vector. Now, you normally do cross products with numbers, right? 5, 1, 2, 30, 0, 2, right? That kind of thing, right? But we're going to do it with these untouched expressions. So stick to the math and you will be safe, right? So just trust the math, right? The first guy is him. So 6t to the 5, 1, 2t. The second guy is him. 30 t to the 4, 0, and 2. Are you comfortable about the setup? Now, I probably need a fair chunk of room, so many i's, take away so many j's, plus so many k's. We're comfortable with that, right? So here goes. Let's get the I. If you cover this guy up, can you see the little 2 by 2 matrix that you should always get? And don't you go major diagonal, take away the minor. That's 2, take away nothing. So 2. Now you want the middle one now, right? That's that one. Major diagonal, take away minor diagonal. The major diagonal is 12t to the 5. Take away the minor diagonal is take away 60t to the 5. Are you comfortable about that one? Major, take away minor. Then you move over here and major, take away minor is 0, take away that guy, which is negative 30t to the 4. Do you see you don't really need numbers to do cross products? Can't you do cross products of anything, right? Variables, anything. Now, make it look pretty. 2, negative 12, oops, almost screwed up there. Those are the same guy, so what's that? That's negative 48. 2 negatives make a plus. 48t to the 5. And that guy, negative 30t to the 4. Are you comfortable with that? That cross product of the first and second derivative might not seem a very, you can't imagine what it could be used for, right? It's surprising that that actually is part of what you need to get what's called the curvature, which is how quickly does a curve curve? You know, if you're in a jet and you do a really steep curve, you might pull 4Gs or whatever they call it, that kind of thing. And this calculation is part of how you would figure that out. There's other bits that go with it, but that's part of it. Well, that was just a one-off question, so you got what you got, right? Now, it might have seemed an eternity ago, but can you remember Calc 1 when they went and said to you, f of x is x cubed, find the equation of the tangent line at the point, 2, 8, that kind of question, right? Find the equation of a tangent line. Well, that's what we're going to do now in number 4. We're going to find the equation of a tangent line. So I'm not going to do any of these two guys because there is only 2 examples. So I'm just going to randomly pick my own. So here is the space curve that you are going to find the equation of the tangent line. And you're going to find the equation of the tangent line at the point P. And the point P is going to be 1, 1, 0. So we are trying to find the equation of the tangent line to this space curve at that point. So can you imagine that this curve that they're talking about is this guy? And that happens to be the point P. Tangent line is what all tangent lines look like, okay? Even in 3D, tangent lines exist. And that line goes on forever, but we're trying to find the equation of it. Now we learnt, oh God, when was it? A few days ago, last week, how to find the equation of a line. Don't you need to know 2 things? Right? If you want to know the equation of a line, you need to know 2 things. You need to know a point on the line, and you need to find a guy called the direction vector. We typically call that guy V when we find him, right? Isn't that the 2 things you need? And then once you know those 2, there's an equation that you put together and you've got, the answer that you're looking for. So I need to find a point on that line. Don't overthink this one. Give me a point on that line.
1, 1, 0.
Would you agree it's the only guy in town, so it probably is that guy? And it is that guy, isn't it? Now, what's going to be harder now is the direction vector. Now, in Calc 1, we would call that the slope of the tangent line, wouldn't we? You'd find the slope of the line. And when you wanted to get the slope in Calc 1, didn't you find the derivative of the function and then just plug x equals 1 or 2 or 22, and that would give you the slope? And then from there, you had an equation. Well, it's kind of similar in many respects. So here is my space curve. And just like in Calc 1, I'm going to differentiate it. And just like in Calc 1, I'm then going to plug in this case, a value of t, and that will give me my direction vector. See, derivative at a point, direction vector, right? Derivative at a point, slope. That's 2D, right? Derivative vector, direction vector. Well, the derivative is e to the t plus 2, cosine t, take away sine t, and 3t squared. And my direction vector, v, is going to be the value of this derivative. Oh, we hit a snag. I don't know what t is, right? I need to know who t is, don't I? If you return back up here, isn't this point also on the curve? What value of t generates this coordinate?
Question, do we set those point two equal to those, well, the derivative equation to those point?
Not the derivative, the original equation. So this guy here to that one. In fact, make your life easy. Isn't the z coordinate, yeah, exactly. Isn't the z coordinate 0? And isn't the z coordinate t cubed? Would you agree the only way that's going to happen is t equals 0? Now, you can check the other two, but trust me, isn't sine of 0 plus cos of 0, 1? Isn't e to the 0 plus nothing, 1, right? So it works. But, you know, find one that makes your life easy, you know, one that's easy to transfer, and you got it. So we know that t equals 0. I put a little bubble up there, because maybe I should have found that earlier on, shouldn't I? Just to make it less hard later. So the direction vector is going to be the derivative at 0. And what does that get me? E to the 0 plus 2. The cosine of 0, take away the sine of 0. And 3 lots of nothing squared. No, I'm going to write that down. It's nothing. That's 1. 1 plus 2 gets me 3. That's 1 take away nothing. And that's just nothing. So we have a direction vector and a point on the line. Agreed? So you want the equation of the line in parametric form? Here goes. That guy, 1 plus 3t. That guy, 1 plus 1t. That guy, 0 plus 0t. Make it look a little bit prettier. 1 plus 3t, 1 plus t, and z equals 0. And in WebAssign, because WebAssign is its own little rules about how it wants answers, that's how you write that guy. They would call that the parametric equation. I would call that the parametric equation. But when you write it this way, that's what WebAssign expects you to do it as. I guess, I mean, how hard would it be to program 3 boxes? I mean, really, can you? Can you just do an x equals box, y equals box, and z equals box? But yeah, I got my little rant over. I am happy. The process that I used to get the equation of the tangent line is more important than this one particular question. So you're going to have a curve, you're going to be told a point, or they might tell you the next time that t equals 0. And if they do, won't you have to calculate the point, right? So whatever they do. You've got an equation for the curve and a point. You know the point because you got it. To get the direction vector, then you differentiate, evaluate the derivative at whatever the t value of the point is. And now you've got the direction vector and you've got the point. Can't you just use your little formula for equations of lines where you know the point and you know the direction vector? Are we good? If I wasn't rushing so much, I would put that first curve into GeoBra and you see it do its squiggle. I would then put the equation of the tangent line and it might look something like this. Can you imagine that might be my curve in 3D space? And this is what my tangent line would look like if I did it right. If I screwed up, there's my curve. And when I put the equation of my tangent line, it's over here somewhere. You see, that had to be wrong, right? I've screwed up. So you could use in a test situation GeoBra to verify that what you've got is correct. Of course, there are lots of ways of getting it wrong. Wouldn't that red line also be wrong? Right. Good, bad. Pause a minute. Any questions? Are we hanging in here, guys?
Yeah.
Right. It's a banner. What my brain thinking? Isn't it like a new universe where Calc 1 just morphed into a three-dimensional Calc 1? Because you're doing a lot of the same processes, like differentiation, plugging things in that you would have done in your Calc 1 world. Right, so chalk that off my list. Can't really figure a name for them, so I've covered them by calling them applications. First one is question 14. And what they tell you here is that you have two curves. And the first one is R1 of t, so you've got a space curve, and it looks like 2t t squared t cubed. And you have a second, totally different space curve called sine t sine 4t and 3t. If I was being pernickety, you really should have called that a different variable, but whatever, we're good. And they ask you to find the derivative of each one. So that's nothing new. We've done that a few times. But so I can move to the next part of the question, I'll do that. 2 power rule 2t power rule 3t squared. Differentiate a sine, you get a cosine. Differentiate the sine of 4t, you will get the cosine of 4t times 4. And differentiate 3t, you will get 3. You comfortable with that? Now you are told that these two curves intersect at the origin. So can you imagine that the first one looks something like that and the second one looks something like that? So right at the origin, these two pathways meet. And we are being asked to find to the nearest degree, right, what angle they cross at. So can you imagine if you zoomed right into the origin, things would stop looking curved, and wouldn't the green one look more like that, and the red one would look more like that? And you're being asked to find that angle. Right, so that's what the puzzle is. And you might think, why did they ask me to do this? Right? Well, can you tell me, why do you think? Can you think of any way of using the derivatives at the origin to find the angle between two vectors?
You remember the cosine and the dot product?
Yeah, can we do that? So I need to know a little, which is why I would have hoped they chose different letters for that, but we can live with that. If the original function, which is 2t t squared and t cubed, if that's at the origin, right? So if it's there, would you agree that means that for this guy, t equals 0? You agree? What value of t would make that become the origin, right? These are what's called position vectors. They're essentially coordinates, right? Now, I can now find what the derivative is at 0. Well, the derivative function is 2 lots of nothing, 3 lots of nothing. So that's what the vector for the derivative looks like on the first curve when it gets to the origin, right? Basically, it's shooting along the x-axis, and that's it. Now, where did I put that guy? I put it up here. The second function, R2 of t, is sine t, sine e4t, and 3t. And that's also going to be at the origin. What value of t would make this the origin?
0, 0, 0. Would definitely become 0.
Right? And so I will now find the derivative of this guy at 0. And the derivative is this fella. So it's going to be the cosine is 0, 4 times the cosine is 0, and a 3. So that's going to be the vector 1, 4, 3. So there is the derivative vector on the first curve. Here is the guy on the second curve. So what we're really trying to do is find out what angle these two things make, which brings us to what Viet was saying, right? We're going to do the dot product. So I want to find at what angle that vector and that vector interact. And I'll call this guy U and call this guy V. Then the cosine of theta is equal to, anybody want to have a shot at trig dot product formula for a missing angle?
That should be the dot product on the top and the magnitude of the both of the U and V.
Does that ring bells, guys? You recollect it? Right. Dot product on the top, 2 times 1, nothing times 4, nothing times 3. Not a lot happening on the top then. Magnitude of this guy eventually is 2. Magnitude of this guy is 1626. So what have we got? 2 over 2 root 26. I guess I could simplify it a little bit. But I'm going to be using the calculator, so it's probably not worthwhile doing that after all. Don't I just find the inverse cosine? And on this fella, the inverse cosine. Oh, make sure you're in degrees. The inverse cosine of 1 divided by the square root of 26 is about 79 degrees, because they want it to nearest whole number, which is actually correct. So if two space curves intersect, doesn't need to be at the origin, but they intersect somewhere, can't you now find the angle at which they crash into each other? In this case, they crash into each other at an angle of 79 degrees.
I had a question.
Yes.
So how did you get a 2 on the bottom? In the
Oh, I found the magnitude of this guy, which is the square root of that guy plus that guy plus that guy, which is the square root of 4, which is 2.
oh,
The magnitude of U. If you've got a vector that's got 2 zeros in the number, the magnitude is going to be the number. Right, that's the end of that one. And then you have another one at 20. Might as well do that one. I'll just do it with different expressions. In question 20, you are told that the derivative of a dot product, so imagine you have a function u of t dot product v of t. right? So you've got two vector functions, u and v, and you take their dot product. When you take the dot product, don't you just end up with a scalar, right? Some t cubed plus 5t squared minus sine t, that kind of stuff. And then you differentiate it. Well, it's equal to the following. U dashed t v of t plus u of t, and I should put a dot product there, dot product v dashed of t. Does that remind you of anything? The derivative of this dot product is that dot product plus that dot product. Does that
It is the
remind you?
chain rule on steroid.
Not the word chain rule, but it is a rule.
Similar to the product rule.
It's just a product rule, or at least similar to it, yeah. And there isn't a quotient rule of this. And there actually is a chain rule version of this, but we don't need to go into that. So let's suppose we tell you u of t is sine t, t and 5. And we tell you that v of t is e to the t, t squared. Well, doesn't really matter what, cosine of t, right? Just for argument's sake. Then the derivative of the dot product of those two is going to be u dashed t. Well, if you differentiate this guy, you get the cosine, a 1 and a 0, dot product with the untouched version of this guy, plus the untouched version of this guy, dot product with the derivative of this guy. So dot product, that guy times that guy gets you e to the t cosine t, plus that guy times that guy gets you a t squared, plus 0 times that gets you 0, so I'm not bothering to write it down. Plus this guy times that guy gets you e to the t sine t. This guy times this guy gets you plus 2t squared. And this guy times this guy gets you negative 5 sine of t. And there might be some minor tidying up, so I should do that. I've got this fella. I've got this fella. Those two get me 3t squared minus 5 sine t, and I can't really do much more, so you're finished. So if someone gives you a formula and says, hey, if you want to differentiate this dot product, here is your formula. Can't you just apply the rules and then plug and chuck? Are we good with applications? The angle that two vectors crash into each other, which was the first one, and how to do a dot product derivative, which is this one. Well, we're getting there. How to evaluate an integral. This is what an integral would look like. That's the integral of a space curve. If I put a little bit more meat on it, 0, 3, t squared, e to the t, 2. Now we've came across the analogy to this thing. Remember when you had to differentiate a space curve, didn't you just differentiate each of the pieces? Great. So if the world was a nice place and things made sense, how do you think you're going to integrate that guy?
Question, can I integrate
Keep talking, yes?
I integrate each of those variables?
It's a little bit long, but would you agree at least it makes sense? Can't you just integrate each one individually? Right, if you integrate this one, you will get 1/3 t cubed evaluated from 0 to 3, and that ends up being 9. And if you integrate this fella, you'll get e to the t evaluated from 0 to 3, and that guy will get you e cubed, take away 1, because e to the 0 is 1. And if you do the last one, that's this one here, well, you get 2t evaluated from 0 to 3, and that ends up being 6. So that guy is the answer to integrating a space curve, which means that integrating has nothing to do with directly the area under a curve anymore. That's not an area under anything, would you agree? It's a vector. So interpreting areas in three-dimensional space is no longer, it's not really a good idea to think of areas under curves in the usual way, right? Just doesn't kind of gist. So here is, it's not perfect, but it's pretty close to what it is. Imagine that you started at t equals 0 here, right? And your space curve done some things and it finished up here at t equals 3. So imagine that's the bit of the space curve you're going to integrate. And to make things relatively simple, I'm keeping the whole thing above the xy plane. Now, if you drop this guy down and this guy down until they hit the floor, can you imagine that you might have a curved wall that looks like that? So far, so good. Can you imagine what that curved wall would look like? It'd be much taller in some places, like much shallower. Now, you could find the area of that wall. Okay. And let's just say, for argument's sake, the area of that curved wall happens to be 10, right? What you then have to do is, on this curve, can you see that any given point in time, aren't you pointing in lots and lots of different directions? Right, imagine all the little tangent lines, right, as you travel along that curve. If you take the average of all these directions, and how do you get the average? Well, you kind of sum them all up divided by the length of the arc, and then factor in this 10. This guy is close to being the average direction that the curve is pointing at over that range. So can you imagine an aircraft that's trying to get from here and it wants to bomb the place over there? The stupidest pilot in the world would fly in a straight line, even although that would get them there quickest. Because if you detect that aircraft on the way, won't you be able to tell where it's going and probably be able to do something about shooting it down? But you still want to get there. Well, couldn't you do a rather convoluted route? That guy is telling you what the blue line is. This is your space curve. Does that help you get an idea of what you're calculating when you get the area, right? Or not? If you don't like that, will you go for, I'm a mathematician, trust me? Will that one work for you too? Okay, let's do some examples of that. So, got 4 of them. I think I could probably do a couple and then we'll move on to the last piece. So, it don't matter what they are, they're all going to be messy. So here's question 17. It's from 0 to pi upon 4. And the guy that we're doing is secant t tan t t times the cosine of 2t and sine squared 2t cosine of 2t dt. Now, essentially what I need to do is find 3 separate integrals. So I'm not even going to try and do it in one go. I'm going to do it in 3 separate goes. And I'm going to have to cut a lot of corners because of time, but hopefully I'll give you a good start. This is Calc 2. This is integration. It's just integration 3 times, right? That's all it is. Right? So it's really Calc 2. Each one of these has to be integrated. This one is just, I have a good memory. Can anybody tell me the integral of secant tan?
That should be secant tan plus a constancy that is unknown. We'll just go with secant.
Just secant. Don't need the unknowns. What method will I use to integrate t cosine 2t? Don't need the answer, but what method would I use?
We remember the Eilate rules.
I don't know that term. What does it mean?
So that is like the order of which one you pick as u and which one you pick as dv, but which I
Oh, okay. Yes. That is correct, but that's not the way I do it. But what you did, what you just said will work. Integration by parts, which is what Viet is talking about. It's just a different approach. You would call it UDV method probably, yeah, and that works fine. Integration by parts. How would you solve sine squared t cosine? Is it cosine 2t? It's sine squared 2t cosine 2t. There we go. What method would you use to solve this one?
I would suggest u subs.
Well, all right, okay, Viet suggesting a u sub. I agree. Someone else tell me what u sub would work.
You could use trigonometric identities.
I wouldn't go there, Lewis. I think that would just add to your workload. Not saying eventually it might not work, but what u sub, since we're focusing on a u sub,
Oh, u sub.
would work for this thing.
I would pick my u as my sine and my du as my cosine, or the sine of 2t and the cosine of 2t. If I make that sine squared become sine 2t squared.
That's the u sub. So you're going to have to look up how to do integration by parts, how to do u subs, and how to remember some trig ones. The other ones you're going to get are much easier, right? Like integrating t cubed, right? Add 1 to the power, divide by new power. Now, if you put that package together, you will get from this one, root 2 take away 1. My pen's going, so switch over. If you do integration by parts, in this one, you get pi upon 8 take away a quarter. And if you do a u sub on this one, it comes out as 1/6. And so the answer to that integral would be root 2 take away 1, pi over 8 take away a quarter, and 1/6. So you have a lot of integrations to get familiar with. Now let me see if I can pick a second one that is a little bit nicer. So again, I'm only going to get to the gist of them. So this is 18. We're doing the integral of 7 over 1 plus t squared. A t e to the t squared and a 5 square root of t dt. And we're going to do basically just a general integral with a plus c at the end. So there's the first one. There is the second one. And I'm going to rewrite the square root as 5t to the half. First one, antiderivative of 7 over 1 plus t squared. Well, you really just need to know what 1 over 1 plus t squared is and times it by 7. So what's the antiderivative of 1 over 1 plus t squared?
That would be the inverse of tangent.
I see nods. Would you agree? Inverse tan. Okay, so 7 inverse tans. Plus this constant, which I'll call C1. What method will you use on this one here? What method would you use to integrate?
U sub.
Agreed. Who's the U sub going to be, Evan?
U equals t squared.
Yep. And can I just tell you what the answer is going to be? Because we're kind of cutting corners here. Plus C2, right? This one I'm keeping for myself because this is the easy one. Isn't this just add 1 to the power and divide by the new power, right? So if you add 1 to the power, you get 3 halves. And if you divide by 3 halves, it's the same as multiplying 10 thirds, right? And an arbitrary constant. So your answer, I'll just call it answer because I don't want to have to write that again, is going to be this fella, 7 inverse tan of t. This guy, 1/2 e to the t squared. And this guy, 10 thirds t to 3 halves. Now, this arbitrary constant I've called C1, this one I've called C2, and this one I have called C3. Why am I not calling them plus C, and plus C? Why am I not doing that?
You said Z was 0, right? Oh, never mind.
No. Why am I not using the same letter for each of these 3 different?
Because it could be different.
They could be different. That's essentially it. Now, that would be a very nice way to do it, right? Separate out the x, the t parts from the arbitrary constants. But this is what they do. They just do plus c with a big arrow above it. Isn't that like a catch-all for just an arbitrary constant vector rather than an arbitrary constant 3 separate pieces? When you're plugging these guys into WebAssign, you know there's a button for putting arrows and things, right? It'll be in the vector menu, right? And you kind of need to find it because it's important. Are we good with that guy? Right, so U subs, knowing various integrals just because you're used to them, all good things. Right, now we come to our final question. If I tell you the derivative, can you work backwards and find the original function? So this is our last guy for today, and this is question 19, and we'll have covered the section. So here is the derivative. It's t cubed e to the t and 5t e to the 5t. And we are being asked to find what the original space curve is. And they tell us that the value of it when t is 0 is 1, 1, 1. Right, we can ignore that for a while. That'll come in at the end. How do you think you're going to take this guy and use him to get that guy. How can you take the derivative, knowing the derivative, and use it to find the original function? What process would you use to go from here to here?
Anti-derivative.
Two people at once, so I never caught either of you. What would you do, Jeremy?
Just integrate.
Yeah. So to get R of t, I'm going to, I'll put it inside that guy. I'm going to do the integral of t cubed. I'm going to do the integral of e to the t. And I'm going to do the integral of 5t e to the 5t dt. Now, if you integrate this guy, it's a power rule. So you'll add 1 to the power, divide by the new power, and I'm putting in my C1 here, right? My arbitrary constant, C1. If you integrate e to the t, you get e to the t plus its arbitrary constant, which I'm going to call C2. And if you do this horrible guy here, right, what on earth are you going to get? You're going to have to do an integration by parts on that. Can I cheat and just tell you what it is? Yes. Can you trust me? If you do integration by parts, you will get t e to the 5t, take away 1/5 e to the 5t. Can you just pretend that we did it? The integration by parts, that's what you would get out of it, right? Now we're 90% of the way home, but I've got 3 arbitrary constants, C1, C2, and C3. That's what this guy's job is. When t is 0, that's what that bit's saying, the answer should be the vector 1, 1, 1. So when I put 0 in here, what do I get? A whole load of nothings plus C1. E to the 0, which is 1, plus C2. A whole load of nothings, minus 1/5 e to the nothing, which is 1, plus C3. And that's going to be the vector 1, 1, 1. So you see what I did? I plugged 0 in here to get this vector. And then I know it has to match 1, 1, 1. Okay. If you can tell me those 3 guys, we are done. Okay, what's the value of C1?
1.
Right? Match with match. What's the value of C2?
That would be a 0.
Right? 1 plus C2 is 1, so C2 gets your big 0. What's the value of C3?
6/5.
Now, if you put that whole package together, you are finished. R of t is this guy plus 1. It's this guy plus nothing, so I won't write anything. And it's this horrible mess because I don't have space or room, plus 6/5. Wow, that was a lot of stuff we covered today. Are you comfortable with most of it? And you can always go back and pause my video and, you know, just take it slow and let it sink in as we go through. But my goal was to get that section done, and I'm kind of pleased that you hang in there with me.